Okay, on to the last question here, which is a digital modulation question. And it says we're looking at a BPSK signal, which means binary phase shift keying, right? So we want to make sure we know what those acronyms mean. Generally, it's something shift keying, but we want to know what it means, right? So we should have two different phases in this graph. So it says, what are the two phases being represented in the signal? And we can kind of see like at certain points on the graph here that there's like a change happening, right? So right there, we see another sine wave. We see that it sort of does something weird here as well. And so we can kind of understand like that there is a shape change happening every 1 millisecond, right? And so if we kind of draw a line and we look at what these shapes look like every 1 millisecond here, we can start to understand what two phases are being used. And to really get this, we want to think about like what a sine wave looks like, right? So this is 0 degree phase, right, or zero phase. If we shift up, and remembering that this whole thing, right, is 360 degrees or 2 pi, right? So that whole thing is either 360 or 2 pi. So if we shift up by half of that, that's at 180, we would be starting like this and sort of going down then up, right? And similar for if we shift up by 90, we'd have a cosine wave. If we shift up by 270 or by 3 pi over 2, we would have sort of an upside down cosine wave, right? So that's what this looks like at 0 degrees and then at pi. And if we look at what our shapes look like, we've got sort of an up and then down and then back up and down again shape. But we're starting from that 0 degree phase, right? And here we've got a down and then up and then back down and then back up again, right? We're starting at phase pi for that symbol, right? So those are the two sort of distinct symbols that we can see in the graph in between these lines. And so our phases are 0 and pi. It's a little tough to see, but really just trying to recognize shapes on the graph as the potential symbols. So then represent the above BPSK signaling scheme as a constellation diagram in figure 2 up here. So we know that around the circle are our angles, right? 0, pi over 2, pi, and 3 pi over 2, or 0, 90, 180, 270, right? And then our lines here are usually going to label voltages, so 1 volt, 2 volt, 3 volt. And if we look at our graph, we go up to 2 volts, we go down to negative 2 volts. So our amplitude for these symbols is 2 volts. So we've got a dot at 0 degrees, and we've got a dot at pi or 180 degrees, right? And they should both be on the same circle since it's binary phase. Amplitude is not changing, frequency is not changing, just the phase is changing. So then part C, if carrier frequency 1.5 kilohertz is used, write a time domain sinusoidal equation for each of the two symbols. So here we're just plugging things into our normal equation, which is Vt equals amplitude sine 2 pi frequency plus phase, right? So we're just going to make two equations that look like this, but represent the values that we've already discovered about this signal. So V0t is going to be 2 volts. That's our amplitude that we found from the graph, right? Sine of 2 pi. F is the frequency we're given, so 1.5 kilohertz, and that should be a T here, plus, and then the phase in this case is 0. So we've got that, and then we've got a V pi T, 2 volts sine. We're not changing the frequency or amplitude, so those stay the same for the second equation, plus our new phase is pi. So that's it for that one. What is the bandwidth of this signal? So here we're relying on the equation that you should have ready to go, which is bandwidth equals to R sim. So how fast are we sending symbols in this chart or in this graph? If we look up, and again, we saw that like from analyzing the graph that we sort of had this up and then down and then back down, this again symbol, right? This sort of shape. And then we have this other shape that goes down and then back up, right? So we have these two shapes, and they're happening at a rate of every 1 millisecond on the graph. So our T-sim that we're analyzing from the graph is 1 millisecond, which means that our R-sim, our rate of symbols, is 1 over T-sim, right, the period. And so that's 1 over 1 ms, which is 1 kilohertz. So our symbol rate is 1 kilohertz, which means our bandwidth is 2 times 1 kilohertz, which is 2 kilohertz. So again, we need to recognize that the carrier wave there is changing at a frequency of 1.5 kilohertz, and that's why we see this sort of like, full sine wave, the period of the carrier itself, right? That's T of the carrier wave, right? And then we see a little more of that same sine wave happen before we change symbols, and then we send the same symbol again here. Here we send the inverse symbol, and then the inverse symbol, and then that first symbol, right? So we can sort of label these as like, 0, 0, pi, pi, 0, pi, etc., right? Depending on what symbol is being sent in that 1 millisecond period. And so our bandwidth is 2 kilohertz. On to the last part. If we transmitted using 16 PSK instead, but kept the bit rate the same, what would be the bandwidth? So first we need our bit rate. We need to know RB. And for BPSK, we have M equals 2, which means N equals 1, right? So we're sending 1 bit per symbol, and we could potentially even label this as like this is a 0, this is a 1. Depends on the protocol what we're sending, but we're only able to send 1 bit per symbol because we only have 2 different values, right? And so here we've got BPSK, M equals 2, N equals 1. And our bit, RB is equal to our number of bits, N, times our sim. So however fast we're sending symbols times the number of bits per symbol, that's our bit rate. And so in this case, because N equals 1, our RB equals our sim. And so to get that RB from the bandwidth, because our bandwidth is to our sim, and because RB equals our sim, this is going to be RB times 2, right? Or 2R sim, substitute R sim for RB. And so if our bandwidth was 2 kilohertz, our RB, our bit rate, is going to be 1 kilobit per second. We're converting between hertz, cycles per second, and bits per second here as well. So then we have to think about what happens for 16 PSK. In 16 PSK, we have M equals 16, and we have, that implies that N equals log 2 of M, right? However many symbols translates into the number of bits we can send per symbol, and that's going to imply that M is 4, right? And we have the values 0, 0, 0 up to 1, 1, 1, 1, 0 to 15. That's our 16 different symbols, right? Represent those values. So 4 bits. So that means then that our RB equals N times R sim. So 4 times R sim, which means that now we have that R sim is going to substitute for RB divided by 4. So if we work that back into our original equation for bandwidth, then we can figure out what our bandwidth is, right? Which is 2 times R sim, which is then we're going to substitute R sim for this value for 16 PSK. So that's 2 times RB divided by 4. So our original RB that we had, that we calculated over here, divided by 4 times 2 gets our bandwidth. So that's going to be 1/2 of 1 kbps. And then we're going to convert to hertz. So that gives us 500 hertz, right? 1 kilohertz divided by 2 gets us to 500 hertz. So that's it. Good luck with the final and/or 12-week exam.